Welcome back. Good afternoon, and we are moving on to the afternoon session of the first day of the conference. We'll be having an invited lecture by Dr. Praveen Walke on 2D nanomaterials-based next-generation photodetectors, following which we'll be having a poster session, and after that we'll be having the second oral presentations of the day. So let's begin with the afternoon session. I would like to invite Dr. Saji KJ, Assistant Professor, International School of Photonics, QSAT, to chair this session.
Thank you, Lakshmi. And it's my pleasure to invite our afternoon speaker, Dr. Praveen Walke. Dr. Walke obtained his PhD from Naples University, Italy, in collaboration with the National Council for Research, CNR Italy, in 2010, based on his works on nanoscale skewed devices for high-sensitive nanoscale applications under the supervision of Dr. Carmine Granata. Before joining for a PhD, he worked in NCL Pune under the guidance of eminent scientist Dr. K. Vijay Mohanan, and also at South Dakota State University in USA at Advanced Center for Photovoltaics with Professor Kukan Kyo. During the postdoctoral training as a prestigious Marie Curie experienced researcher, he developed high-K dielectric materials using oxide nanolaminates for capacitive devices. During 2012-13, he worked as an RA and obtained Best RA Award in Inter-University RMC at Department of Physics, University of Pune. He has awarded UGC Raman Fellowship for 2015-16 to pursue his postdoctoral training in University of California, Berkeley, under the guidance of Professor R. Ramesh, former director of National Nano Initiative Program, USA. Since he joined Mumbai University in 2013, he has established a research group working on energy materials, thin films, and nano micro devices. He has published more than 40 research articles in international journals and a couple of books to his credit. He is a reviewer of several reputed journals and a member of various national and international societies. His research in energy storage, especially fast charging, lightweight, and long life batteries, has attracted media attention. He is now working as an assistant professor at National Center for Nanoscience and Nanotechnology, University of Mumbai. With this brief introduction, let me welcome Dr. Praveen Walke for his talk on 2D nanomaterials-based next-generation photodetectors. Over to you, Dr. Walke.
Thanks a lot. Let me thanks organizers for giving me an opportunity to be here in this event and connect to all of you through some flavor of our future further research. Thanks a lot, Professor Saji, for such a extensive introduction about me. So today, I'm here a little bit giving you a flavor about the 2D nanomaterials for next generation photodetector applications. So here are outline of my today's presentation. First, I will introduce something about the photodetectors. Then why these 2D nanomaterials are important in terms of photodetector applications. Then we'll see one example of graphene photodetector. Then we'll just have a brief overview about two-dimensional engineering approach to improve the photodetector performances. Then we'll show you some one of the example of zinc oxide nanosheets which developed in our laboratory for photodetector application. And then I will conclude my presentation. So these are the outline of presentation. Let's have a look on what is photodetectors. Photodetectors are generally semiconductor devices where it has to detect the photon presence, right? And therefore it is called a photodetector. Usually in photodetector, what happens? The optical signals get transferred into the electrical signals, and ability to transfer the optical signal into the electrical signal is very important. A very important figure of merit to the photodetectors. So usually what happens is that if you incident a photon or light on the semiconductor devices, you will find out there is a generation of electron hole pairs, and once it exceeds the band gap or energy exceeds photon energy exceeds the band gap energy, then probably you will get these electron hole pairs, and this is basic mechanism of this photodetector, working principle of this photodetector. Usually, this response of these photodetectors are proportional to the power of the beam which you are incidenting on that particular detectors. So these are the brief overview of the photodetectors, but what are the general applications of the photodetectors? So these photodetectors can work in a different range of the frequencies, wavelength, different wavelength range, let's say UV visible, in a near infrared, then short wave infrared, mid wave infrared, long wave infrareds, right, far infrareds and terahertz. So these are the different different band ranges of these wavelengths, and based on that, how your photodetectors are responding to those particular ranges have different applications. So people usually use these kind of detectors for the pollution detections or sensors, then imaging, then bioimaging, then telecommunications. Nowadays, these quantum computing and telecommunications, IoT, Internet of Things. So all those chemical analysis, usually we use the TIRs and all the stuff, thermal imagings, medical imagings, and so on. So these are the several applications of the photodetectors, and therefore development of the photodetector and improving their performances become very important in the scientific community. Right. So let's have a look on what are the needs to improve the performance of the photodetector in terms of it should make a smart photodetectors, or we can say the next generation photodetectors, right? So here I have listed some of the points which is important in order to see the performance of the photodetector for the next generation. And first of all, its sensitivity should be improved, or sensitivity should be high enough to emission wavelength range of received light signals. Then second point is that the photodetectors should have the minimum noise to signal ratio, right? So there should be the very less noise in photodetectors. Third one important parameter is the fast response. So the responsivity of your devices should be very high in order to handle the desired data, or speed of that photodetector should be very good. Another important parameter is this temperature variation should not affect on your sensitivity of the photodetector, because as long as you are incidenting the photons, then thermal excitation may happen and it will disturb the photodetector performance. So there should be enough insensitivity towards the temperature variations. So and also it should be compatible to physical dimensions of whatever the applications you want to do. The physical dimensions of, let's say, if someone wants to use in fiber optics, these kind of photodetectors, then its compatibility should be good, right? So they should be compatible to the flexible substrates and silicons and so on. So compatibility is another important factor in next generation photodetectors. And another thing is cost effectiveness. It should be the cheaper, right? So every technology needs to become cheaper, and that is another important thing should be looked into. And another important factor is like a long operation lifetime. So lifetime of those photodetectors should be very high. So these are important parameters need to improve in the sense to get a very smart photodetectors. So in terms of photodetector performance, right, as we have seen before, there are several important things, but there are some important parameters which should be considered in case of photodetector. And photodetector, for example, quantum efficiency, right? So quantum efficiency of your photodetector should be quite good, right, in terms to have the smart photodetectors. And what is the quantum efficiency? Which is nothing but the primary electron hole pair created by the incident photons, right? So the ratio of electron hole pairs generated per photon, right? So the rate of electron hole pair generation by per photon incident on the photodetector, and that ratio is nothing but the quantum efficiency, and that should be quite good in terms of having the smart photodetectors. Then another thing is responsivity. So response of your photodetector should be quite good, and that response can be measured by the ratio of output current to input optical power. Then third important parameter is the response range. So usually photodetectors have specific range, and next generation photodetectors needs to have the broad range spectrum working operation of that photodetectors, and therefore the range of wavelength should be quite bigger in order to operate those photodetectors, right? So wide range photodetectors are need of the future generation. So another important factor is the noise. So the level of noise should be quite less in terms of having a smart or responsivity and sensitivity of your devices. So you need to reduce the noise, and in that sense you should have a very low level of input lights, right? So it should operate at very low input light with very less noise, right? So this should be another figure of merit of this kind of devices. And important parameter is response time. It should be quite quick. Your smart sensors need to be very quick, and which can respond to the variation of input light intensities. So these are the important parameters need to be considered when you are thinking about photodetectors. So the important thing is why people are thinking about the 2D nanomaterials or conventional semiconductor detectors, right? So as we know, the conventional semiconductor detectors like silicon or 3-5 semiconductors have less band gap, and that can have UV visible range and different wavelength detections, and the detectivity of those traditional semiconductor detectors is in the range of 10^10 to 10^13 joules. But the problem with these conventional semiconductors detectors are nothing but they are suffering for cryogenic temperatures, and they are inflexible, right? So they are not flexible. Flexibility issue is there. So if we are considering about the 2-dimensional nanomaterial based photodetectors, so the advantage of having 2D materials for these photodetectors are nothing but they can have the broadband detecting ability. The thing is, this kind of 2D materials has high mobility, and therefore, they are showing the high speed performances, or responsivity would be quite good. And they are quite sensitive. So sensitivity of those 2D materials is very high. And another thing is it is compatible to the flexibility, and it has a flexibility potential. So these are a number of advantages of having 2D nanomaterials for photodetector applications. And here you see there are various 2-dimensional materials. First one start with the graphene. Graphene is the first 2D material explored by the scientific community. And later on, people have explored the various 2-dimensional materials. They have different structures, and each 2D material has its own structure, and which is really favorable for photodetector in different ranges. So we will see some of the example over a period of time. But let's have a look on graphene photodetector. So what are the advantages and limitations of these graphene photodetectors? Already, people have explored graphene for the photodetector applications. So the advantage of having the graphene is it has ultra broadband photodetector because of gapless band structures. So there is no zero band gap almost, right? So graphene is a zero band gap structure, and therefore it has ultra broadband photodetector, right? So the absorption, and therefore what happens is the absorption spectrum, right? Absorption spectrum of this graphene covers almost ultraviolet to far infrared range, right? So it is a wide spectrum covered by this graphene. So these are the advantages of the graphene photodetector. But another important advantage is that it has very high mobility, right? A high mobility around 10,000 centimeters square per volt per second. And its optical absorption coefficient is almost 7 into 10⁵ per centimeter over a broad bands. So these are the advantages of having a graphene for the photodetector applications. But the limitation with these graphene photodetectors are, the lifetime of photo-generated carrier is very short, right? Because the channel is very short, and therefore, as so long as you generate the photo, generated carriers, and they recombines very fastly. Right. Same thing happened with the ultra fast hot carrier combinations. As soon as you incident the light on it, there is the vibration, and hot carriers can easily recombine in these kind of the graphene structures. So that is another limitation of graphene photodetector. But you see here the graphene PN junction. People have tried to make some, graphene PN junction for the photodetector applications, and which suffers from the small area of the effective junction. So that PN junction effective area is very small, and as there is a small junction region, then there is a very weak optical absorption happens, right? And if there is a weak optical absorption in that, then ultimately it affects on the responsivity, and the responsivity limit will be very few milliampere per watt. So these are some of the limitation of the graphene photodetectors and some of the advantage of the graphene. So what people have done, so this responsivity limit, right, which is very low because of the small optical absorption of monolayer of a carbon atoms. So researchers have tried to integrate these colloidal quantum dots, right, colloidal quantum dot into this absorption layer, and they have observed that it improves the responsivity, right? The responsivity of graphene photodetector up to 1 × 10⁷ ampere per watt. But as there is an improve in responsivity, but the spectral range of the photo detection is reduced. So as we have seen previously, there are the several parameters which need to consider in case of the photodetectors, right? But all the parameters, if you are trying to improve one parameter, the second parameter should not be compromised, right? So once you improve the one parameter by keeping another constant, that would make sense. But here, the colloidal quantum dots integration has improved the responsivity one side, but the other side, it has reduced the spectral range, right? And that is not expected. And therefore, this kind of strategy may not be very good to improve the photo detection performance of graphene. So then another important strategy people have been used is like, double layer heterostructures. They use the double layer heterostructure by graphene. So they use the two layer of the graphene separated by the separator or small thin tunnel barrier. And this detector is based on phototransistor, right? So let's have a look on that kind of device here. You see the image here, right? The Liu et al., who has published this work in 2014 into the Nature Nanotechnology. And what they have done is they have simply used two graphene layers, which are separated by the thin tunnel barrier, right? And the performance of this photodetector can be tuned by changing the tunnel barriers. So if you change the tunnel barrier, you will find out the performance of the photodetectors might tune, right? So in the first figure, you can clearly see the illumination power dependence of the photocurrent here in the C under the radiation wavelength of 3.2 in the different gate voltages. So in the graphene, there is, so energy of the graphene here. You can see the band diagram of one graphene layer, another graphene layer, which is separated by the tunnel barrier. And as soon as light illuminates on this kind of photodetector, then what happens is that electron hole pair generates, and that generated electron hole pairs, you will find out that, this will generation of the electron hole pairs, right? That is photo excitation. And this laterally, it will transfer holes from one layer to another layer through these tunnel barriers. It means there is a tunneling happening between these kind of stuff. Right, so this is another important phenomenon that people have tried, and they have found that it can operate at the wide frequency spectrum or wide wavelength range. And then they have measured this photocurrent with respect to the power, right? And then they have found that if you increase the power of the light, then you will find out the photocurrent generation is linearly increased, right? And that has to be with respect to gate voltage. So if you tune the gate voltage, then you can easily tune the photocurrent generation with respect to this. So similar thing, under the optical illumination, what happened, that photo excited hot carrier generated at the top layer, right? Top layer of the graphene, and which tunnels into the bottom layer, right? And that is charge, there is a charge build on the gate voltage, okay? And this phenomenon strongly called as a photogating effect on the channel conductance. So this photogating effect already people are trying in a different variety of layered structure as well. So it demonstrates the room temperature photo detections, because temperature is another important parameter. And if your photo detectors works at the room temperature, that makes very good sense. And especially in the wide range of the spectrum from visible to mid-infrared region, right? And this two-layer structure, already people have shown that mid-infrared shows high responsivity up to 1 ampere per watt, as it is required by the many applications, especially broadband IR detectors, right? So broadband IR detectors require such kind of mid-infrared responsivity. And then these graphene-based hot carrier optoelectronics applications can be also use such kind of bilayer structure of the graphenes. Okay, so other than graphene, there are so many number of two-dimensional materials. So, for example, the transition metal diisocogenates, then black phosphorus, hexagonal boron nitrides, and so on. So, these different 2D layer materials can perform differently because of their distinct electronic and optical properties as compared to the graphene, right? And they are the semiconducting in nature, and graphene is semi-metallic, right? So, these for example, let's consider the MOS2, right? MOS2, which is highly explored material by the scientific community. And this MOS2, which is typically TMD material. But the beauty of this material is that if you change the thickness of this MOS2 layers, right? If you change the number of layer of MOS2, then you can easily tune the band gap. It is same like, changing the size of nanomaterials. So here, the thickness dependent band gap tuning is possible in MOS2, right? So this is a very good advantage of these 2D materials, so that you can easily engineer the band gap, and so that you can engineer the photo detection properties, right? So, and compared to the graphene, what is the advantage of MOS2? MOS2, which has a very high absorption coefficients of the visible range because of direct band gap, right? So MOS2 has a direct band gap, and therefore it shows absorption coefficient, a very high absorption coefficient at visible. So here is an example where Kai-et.al has reported already in the advanced materials. So here you see this MOS2. So this MOS2, if you change the number of layer of MOS2, then how the absorptance with respect to the wavelength that changed, right? So this absorption capacity you see here, with improving the number of layers, you find that the absorption coefficient is quite good, right? So absorption is improved with the number of layers because of light matter interaction, or lattice interaction, light matter interaction, and therefore the absorbance with respect to wavelength is improved. And then you can see here the responsivity with respect to the wavelength. Initially, you find in UV range, the responsivity is quite high, right? So which is almost 50 milliampere per watt. And if you increase the wavelength towards the higher wavelength, you will find out it is drastically reduced in the UV range, and then later you will find out it is up to 30, right? 30 milliampere per watt at highest wavelength, let's say 2000 nanometers and so on. Similarly, you see the detectivity of that particular photodetectors, and at UV range, you will find out the highest detectivity is almost 1.5 into 10⁹ joules, right? And it will reduce with respect to increasing the wavelength, but still you will find out it is almost 0.5 into 10⁹ joules, right? So this is a very good figure of merit of these kind of two-dimensional materials, and the engineering of the layers give you the control over the photodetector properties. And therefore, people are thinking about the various two-dimensional materials which can easily tune the properties of photodetectors. So based on your application, what application you require, based on that, you can tune the two-dimensional material properties. You can select the two-dimensional materials and get desired photodetector performance. So here, let's just have an overview about how people are developing the strategies for 2D materials, photodetector, and how they are trying to enhance the device performances, right? So this is a broad overview about the various strategies people have been used, and I have collected all those from some of the references. So here you see This is the 3D view of a vertical PN junction of MOS2 nanoflex, right? So PN junction here, the P-type doped AuCl3 and then MOS2. And this is the homogeneous PN junction across the channel, right? So here what happened is, this PN junction usually, these can act as a photodiodes, right? And then the current generated as case of photoelectric effect. And here you see in the B value, they have found out the ID current with respect to time, and with respect to the different gate voltage, they can tune the responsivity and the sensitivity as well, right? So here it shows the 100% performance and almost 30% responsivity of this device just by making the PN junction, vertical PN junction and homogeneous layer. So this is one of the example which has already published in Nature Communications. So, but you can modulate the performance of this device just by changing the gate voltage. And another strategy people have tried to use is, they are doing the heterojunctions. So here they have used the two different 2D materials, right? So each material has its own features and they have their own distinct properties. So how those two distinct properties are embedded to have the better photodetector performances, right? So this is one of the example where people have used the MOS2 is the one layer and WSE2 is the other layer, right? And here you see the photoconduction. Here you can find out the performance in this figure D, and as soon as the light incident illumination of the light, you can find out that VDS can control the performance, right? So this performance can be controlled, and here you see in the inset of the figure, current versus time, and you find out this response is very fast, right? So the responsivity is quite good. So speed of this kind of two-dimensional photodetector is improved just by making the two different sandwich of the two different 2D materials, right, on each other, and the performance has improved drastically, right? So this is a milliseconds, you see 0 to -3 milliseconds, and this was in seconds, right? So as compared to this strategy has improved speed of this, or you can say the responsivity has been improved. Okay, so let's have another example here. So here, the third strategy of the 2D material is that they have made the, okay, so this is a device made up of MOS2 and MOT2, right? So the two vertical junctions, you can call it as a vertical junctions. Okay, and then this overlapping of MOS2 and MOT2. So the area of the overlapping can called as a channel. And so if you change the channel thickness, okay, or if you change the channel length, then you can easily tune the properties. And this kind of device, so MOS2, MOT2, in this case, what happened is MOT2 has a low band gap, and therefore most of the light spectrum has been absorbed by MOT2, right? And you can find out this conduction band of MOS2 and valence band of MOT2 will have, the highest conduction band of this and valence band of this. You will find out the energy gap is just 0.6 electron volt, right? And therefore it can operate at NIR region, right? So 155 nanometer wavelength range. So this device can work at wide spectrum as compared to these two devices, right? But let me compare these first two devices. Here, this is the homogeneous PN junction, and this is the heterojunction, right? So what is the importance of having this PN junction and heterojunction is that quantum efficiency of this device, which is quite less. It's almost 0.1 to 1%. But in this case, these people have observed quantum efficiency up to 12%, right? So improve in quantum efficiency just by changing the strategy, just by using the two different 2D material. And here, what happens is this MOTE2 is absorbing most of the light spectrum, and therefore the wide spectrum range has been covered in this kind of devices as compared to first two devices, right? So this is the advantage of this, and it can be controlled by the channel length or channel you can say the channel length only, right? So fourth important thing people have been tried to use is that they want to improve the absorbance of those kind of sandwich layers. Right here, it was just 0.6 electron volt energy band difference. But if you try to sandwich MOS2 with WS2, and here you can find out there is just 0.8 electron volt energy gap between these two interfaces. And there is another important thing is that at the interface, the transport property, so transport of electron from one layer to the other layer will help you to avoid the recombination, right? So the transfer will help you to improve the photo detection performances rather than loss because of the recombinations, right? So here, this MOS2 and WS2 is another important parameter where they have found out 0.8 electron volts. But what happened? This Wang et al. They have proposed that if you add the gold layer, right? If you add the gold nanoparticle in between the sandwich at the interface, then what happens is that your spectrum range will enhance a lot, right? So your spectrum range is enhanced just by introducing the gold nanoparticles. And you can see here the IV measurements at various wavelengths. You will find out from 532, it shows very good current voltage characteristics, but still it sustained up to 10 is to up to 1030 nanometer, right? So there is a still photocurrent generation happen, though it's not very high responsivity, but still it is there. And therefore, this strategy has helped you to widen the gap, widen the range of your wavelength, right? So these are the four important strategies people have been used. So we will later figure it out how these kind of strategies are differentiated with respect to their physical phenomena, right? So there are the different categories. We can differentiate those different strategies into based on their physical mechanisms, right? So first one is the photovoltaic effects observed in those detectors. Another is photoconductive effects. Then later on, photothermoelectric effects or photovolumetric effects, and surface plasma wave assisted effects. So these are the four different categories can be done in this kind of various engineering of 2D materials based on their physical mechanisms. So photovoltaic effects, what happened in the photovoltaic effects are, so photo generated carriers, right, which emerge and transpose under the action of internal electric field. So if you, as soon as you incident the light, if you irradiate light on the two-dimensional material, what happens? The photovoltaic is generated inside the 2D materials. And this kind of effect can observe in different heterojunctions, homojunctions, and Schottky junctions, right? Like solar cells, people are, those who are working in the solar cell areas, they can understand this photovoltaic effect or photoelectric effect. And you can find out these are the IV characteristics in that, right? Where you will find out open circuit voltage and short circuit current, right? So this phenomenon of the photovoltaic, where, this charge carrier generation, right? Electron hole pair will generate as soon as you incident a light. The wavelength of or energy of that photons should be comparable or higher than the band gap energy of the band, right? And then immediately the electron hole pair generates and it will generate the current across the device, right? So this can be applied to different photodiodes, phototransistors, and so on. But the advantage of having 2D materials photodetector, where a photovoltaic effect is there, where we have very high carrier mobilities and high Fermi speed of the 2D materials, right? And this kind of excellent high frequency response characteristic of this photovoltaic effect in the two-dimensional will be very useful for the optical communication, optical modulators, and ultra-fast light detection applications. So this is one of the category based on the physical mechanism and how this photo response can be observed by photovoltaic effects. Another important criteria was, or physical mechanism was, photoconductive effects, right? So in the photoconductive effects are the conductance of the semiconductor, which can be changed just by incidenting illumination energy, right? Incident illumination energies. And you see the incident photon energy get absorbed by the semiconducting material here. So in the dark, you will find this is the energy diagram, energy band diagram. And then as soon as the illumination, if your photon energy will be comparable or which is higher than the band gap energy, then ultimately the electron hole pair generated and then current can pass through that, right? So you can see here this gate voltage, how it controls the current between drain and source. And here, this is simple IV characteristics in the dark as well as in the illumination. And you will find out the photocurrent is much higher in this case, right? So this is the simple photoconductive effects. And most of the time people use this photoconductive effect in photodetector applications. So another important parameter or another important mechanism was photothermoelectric effects. What happened, this kind of effect is observed because of the Seebeck effects and this thermal effect, which can cause a heating effect in illumination light. So what happened, there is strong electron interaction in 2D materials happens. So as soon as you incident the light on the metal, then what happens is that metals get heated and the hot carriers can pass through this semiconductor, and there is temperature difference between this and another electrode, and therefore there is mobility of this semiconducting 2D layer will improve, right? Here you see the temperature difference of this and this electrode, and through the semiconductor, what happened, that mobility of the charges will tuned because of heating effects, right? So the electrons and hole pair get generated as soon as we irradiate light on that particular 2D materials. But in that case, what happened? The heat of 2D material, which can fastly carry within a short time, right? And therefore that hot carriers, which can improve the temperature of that particular system, like lattice vibrations, and your lattice energy will improve so fast, and therefore the mobility will be very high, right? So it can hardly dissipate to the lattice, and therefore what happens is that high rate of temperature difference, which can produce the electromotive force, so that your charge moves from one temperature difference to another one, right? And thus you can form the photothermal electrical effect, which can generate in the 2D materials. And here you see the IV characteristics under the dark and under the light illuminations, right? So this is the just temperature difference because of the hot carrier. Okay. Then another one is photobolometric effects. So photobolometric mechanism, which is directly related to heating effect of the incident photons, but which can lead to the carrier mobility change into the 2D materials, right? As we have seen just in the previous case, the same thing happened in the bolometric effect. And the sensitivity of such a 2D material bolometric detector can be found out by the thermal resistance of RH is equal to dt by d. And another important thing is the response speed of the detector and sub-millimeter wavelength of the 2D, the heat capacity, which can far exceeds the limit of LIR photodetectors. And therefore, the radiation heat detectors has an advantage of the light detection of LIR band, and therefore it can be realized in alkyl bolometers, right? So last and important physical mechanism part of this is a surface plasmon wave assisted method. So in the surface plasmon wave assisted, as we have seen in the previous example, where gold nanoparticles were introduced in between the 2D, two different 2D material sandwich, like at the interface, they have introduced the gold particle, and surface plasmon has been as soon as the light incident on that, because of the golden surface plasmon resonances happen, right? And in that case, what happened, the interaction between the 2D electron gas and plasma wave of the 2D materials, that field effects happen. But in this case, what happened, if your plasma wave is weakly damped, then what happened is plasma wave and 2D electron gas would form the interference, right? And they realize the resonance detection mode for the plasma waves. But if plasma wave get overdamped, right? Overdamped, then what happened? Wide band detection mode observed in this. And this is the signal intensity of resonance detection mode, which is 5 to 20 times higher than this broadband detection mode. Okay. So signal intensity in case of resonance is quite high. And therefore, this kind of mechanism, which provides the rectification for altering electric and benefit, and which is really benefit for terahertz detections usually. So it's a very high range of the terahertz detection. This mechanism has formed. So you see here, the people are trying the various methods, and what these techniques are fall into which kind of category. So in photovoltaic effect category, you see, if you have the sandwich between the vertical layers, if you have the sandwich between the PN junction of vertical layers, if you prepare the heterojunctions in PN junctions, and if you have the homogeneous PN junctions, so this falls into the photovoltaic effect category. If you see the photoconductive effect category, there is, people have used the lead sulfide quantum dots enhanced structures. Then people have used the nano two-dimensional material and sandwiched between the different nanostructures as well. Then bilayer enhanced absorption. So if we have the two different layers, then which can enhance the absorption, as we have seen that, one has low band gap and one has higher band gap. So low band gap can be the receiving end, and it can absorb the more things and it will transfer to the other layer. And another one is a floating gate enhancement. So you can tune the gate and definitely you will find out, the photoconductive effect can be tuned. Then photothermoelectric, people have tried with the vertical gradient enhancement, MOS2 electrode PTE. Then there are the suspended graphene, one of the important example, and single bilayer enhancement also is come into the thermoelectric effect. So surface plasmon enhanced effect, people have tried the metal SPP enhancement. So you can just dope the metals or have the nanoribbon, graphene nanoribbon enhancement. So you can just put the nanoribbons in between. You can have the asymmetric metal contacts to your photodetectors, or AU nanostructured enhanced. So you can just put gold nanostructures inside the layers or inside the channel, and you can find out the surface plasmon wave assisted effect is also. So these are the different physical mechanisms which controls the photo detector performances in the different various scales. Okay, so let's look at metal oxide semiconductor based photodetectors. So what are the important things in metal oxide based photodetectors is, so there should be the charge carrier engineering is required to improve the performance, and these are the future development trends what we'll see at the right side. But first of all, let's have a look on charge carrier engineering. So carrier engineering is that there should be the carrier generation, right? One part is, you should have very good 2D materials or metal oxide materials to generate the charge carriers. Then you have to separate those charge carriers, systematic separation. The recombination should be reduced, or recombination should be minimized. And then carrier transport should be very good, so that your ohmic contacts with your 2D materials should be very nice. And carrier collective materials should having very high mobility. So these are the important parameters in case of charge carrier engineering. But in case of the future thing, what people are thinking about is the self-power photodetectors. So in the self-power photodetectors, usually what happens, if you have the two different 2D materials, or if for example there is a vertical junction, right? So in the vertical junction, what happened, the photo one is another band gap, another is another band gap, and then therefore there is a charge transfer happen across the interfaces, right? And due to that charge transfer, there is a electric field generated or developed across the interface, and that electric field is driving the charges, right? And therefore such a system, without applying any external potential, it can have the internal electric field which will drive the charges across the interfaces, and therefore such kind of self-power photodetectors people are trying to use. Another is two-dimensional van der Waals junction photodetectors. So I will show you some of the example of the 2D van der Waals junctions. For example, MOS2, we have seen the different layers MOS2. So similarly, people are trying to have the van der Waals junction between the deflection layer, and they can find out the good photodetector performance. And another important fact is a broadband photodetectors. So the photodetector layer should operate at the various band range, and this is another important task people are trying to develop across. So let's have a look on here the van der Waals heterojunctions example here. So here you see WS2 and WSE2, or MOSE2 and WS2, the vertical junction has been formed here. And this vertical junction, you say the band diagram in the inset here, how this band diagram, and in the dark current, you see the high V characteristics over here. So it is in the dark current. So as soon as the light illuminated with a different power, you see here, as you are increasing the power of illumination, light, so you will find out the photocurrent generation is quite higher, right? So large photocurrent is generated, right? So, and this on-off ratio is improved with respect to the power. So here in the another figure, you can easily see the responsivity with respect to the incident power. So the responsivity is completely decreasing, if you are increasing the incident power, but at the same time, the generation of photocurrent is quite good if you are increasing the incident power, right? So therefore, this is characteristics of the photodetector in if you have the vertical junction of WS2 and MS2. But what is the role of the gate voltage? And here you see, if you increase the gate voltage from 1 to 4 volt, you will find out the photocurrent generation is improved and the time is almost same, right? So and time. So, but the only thing is on-off ratio, so responsivity is very high, right? So the gain of that particular photo detector would be very nice. And let's come to one of our material, that is mesoporous zinc oxide nanosheets at room temperature. So we have prepared this mesoporous zinc oxide by using the simple chemical bath deposition method. And you can see here, these are the different flakes, right? So these are the nanosheets kind of morphology of this zinc oxide. And this TM can show you, this is quite good sheets as observed, and that is polycrystalline sheets. So here you see we have prepared this one. So this is porous sheets. Just by annealing this MOS2, just by annealing these zinc oxide nanosheets, we have found out there are the different pores has introduced, and therefore these mesoporous zinc oxide nanosheets. So we have tried to check whether this normal zinc oxide sheet or non-porous only zinc oxide sheet as synthesized, and this annealed mesoporous zinc oxide nanosheets, what is the difference between that? Okay, so before going to see those difference, we have just done the XPS measurements on both the samples, like normal pristine zinc oxide and mesoporous zinc oxide. So here in the both case, we have found out the zinc P3/2 and P half peaks, 2 peaks. But here in this oxygen, especially, we are very much interested in the oxygen because zinc having adsorbed oxygen on the surface, but here this is OL is the lattice oxygen peak we have observed, right? And this is you just do it. So this is lattice oxygen, and this is chemisorbed oxygen. But if you annihilate it at particular temperature and introduce the pores in that particular sheet, you observe that this is the lattice oxygen. And you have here, you see chemisorbed oxygen is quite high in this case, but here chemisorbed oxygen is drastically reduced, and we have found there is a valence oxygen peak here. So oxygen valence peak in this has been observed. That means after annealing, you have reduced the oxygen content of this adsorbed oxygen as well as the oxygen content in that, and the pores has been formed. So here, let's have a look on these photodetector properties of the zinc oxide, right? So these two are the different things here. This is the pristine zinc oxide, and this is mesoporous zinc oxides. And you see here in the dark and in photo here, so photocurrent generated in this field, in this pristine zinc oxide structure and in mesoporous zinc oxide structure. So we have observed that performance in mesoporous zinc oxide structure is quite good, right? And here you see this is just a current versus time plot, right? And where you can find the response time is 4 seconds and recovery time is 6 seconds, right? So here is response time has been increased, so it speed up the process of the photo detection in case of mesoporous and which is having less or which is having the oxygen deficiencies as compared to this one. And here you see the light on and off. If you on and off this light, you will find out this is responsivity. And as compared to this pristine, you can find out this annealed sample, which has very good number of cycles, and stability is quite good in this sense, right? So what is the advantage of doing all these things, right? But what happens, see, in the dark condition at room temperature, what happens? Your chemisorbed oxygen molecules, which can take a free electron from the conduction band of zinc nanostructures, nanosheets, and which can create the space charge layer, right? Space charge layer with a low conductivity near the surface. And here this reaction happens. You have the atmospheric oxygen, and you adsorb oxygen, and you take the electrons from the zinc oxide, and you can find out this adsorb oxygen species. And under the light illumination, there are two probable mechanisms which are happening in the photocurrent. First one is, photon energy of the light, which is more than the band gap, which generates the electron hole pairs, right? And under the constant bias volt, what happened that unpaired electrons are collected at the anode, right? And which increase the conductivity of the cell, right? By reducing the space charge region. Another one is desorption of the chemical, chemisorbed oxygen molecules from the surface, and which can recombine the whole, right? And which is returning the electron to the conduction band. So these are the two probable mechanisms which has improved the performance of mesoporous zinc oxide, which has annealed and has a oxygen deficiencies as compared to the pristine sample, right? So, but the advantage of having this thing is that we have observed this phenomenon and high responsivity at room temperature, right? So this zinc oxide is very versatile material and has a good band gap, right? Wide band gap semiconductor, but still it has shown just by modulating, making into the two-dimensional structure, having the oxygen deficiencies, by just simply annealing, give you the room temperature very high response photodetector applications, right? So I think I'm just crossing the time. So just come to the conclusion of my today's presentation. So the basic conclusion is that we have found out, though there are high-speed graphene photodetectors people have tried, they have suffered because of the low responsivity, and they have the large dark current due to their high mobility and inferior excitation separations. And therefore, in order to tackle those problems, people have tried to use the two-dimensional materials, right? But they are engineering the material, right? Especially in case of graphene, they are opening the graphene band gaps, try to open the graphene band gaps by introducing the defects and so on, or enhancing the interaction between the graphene and 2D materials and light through different material engineering, heterojunctions, right? Different layered materials, introducing gold nanoparticles inside the channel layer and so on. But nowadays, people are thinking about the vertical heterojunctions and field effects enhanced functional strategies, which can trigger the efficient photodetector properties. So with this, I would like to acknowledge my research group, my PhD students and postdoc, and my collaborators, my colleagues, and the director. And I would like to thank all of you for listening this talk very peacefully. Thanks a lot. If anyone have a question, I'm happy to answer.
Thank you, Dr. Praveen Volke, for your wonderful talk on two-dimensional material-based photodetectors. And we have a couple of questions in the chat box. So let me read it out. One question is, which is the material in which maximum quantum efficiency is reported?
Actually, one single material doesn't show very good quantum efficiency. So people are trying to engineer the various materials, bandgap engineerings to tune that things. But I have found that nowadays the M-hexene material is showing very beautiful quantum efficiencies for the photodetector applications, which is almost 25% or so.
Okay. And another question, what happens when the chemisorbed oxygen is removed by annealing? Does the oxygen atoms remain in the lattice and increase the lattice oxygen?
No, actually, chemisorbed oxygen get separated, or they can removed from the surface, right? And they are not induced into the lattice actually by just annealing.
Okay.
And therefore, the space charge region has been reduced, and lack of oxygen or oxygen vacancy is created into the zinc oxide structure just by annealing this zinc oxide.
Okay. And another question, how spectral range is broadened in next generation photodetectors?
Spectral range, as I said, people are trying to tune the property just by making the heterojunctions, let's say. And heterojunction, people are, as I showed, there are the three different techniques of, self-powered photodetectors, right? Is self-power or layered photodetectors. In that case, what happen, light matter interactions will be controlled, and therefore the range has been introduced. So let's say if there are the various band gap of various films, two-dimensional nanomaterials are stacked together. So you will have the absorbance. Absorbance will be very high because every layer will absorb the various band of various band wavelengths, right? And therefore the total absorbance will increase, and therefore the photodetector performance will be quite high. So photocurrent will be increased. So there is a stacking of different 2D materials in order to improve the absorbance, and which can ultimately enhance the photocurrent.
Okay. And there is one more question, and that I think that is regarding the XPX spectrum. Can you please explain what OV is?
Okay, let me go to that. This one. So what was the question? OD.
Yeah, can you please explain what is OV? I think it's oxygen vacancy. Is it?
Yeah,
I think it is related to the XPS. Yes.
Yes. Here. This is OV. OV is, there is a lack of oxygen or oxygen vacancies as there, and because of the vacancies, there is a stretching and bending, right? So if oxygen has removed, the bending has happened, and because of the bending, you will find out at particular binding energy that peak has been introduced. And this peak, if it's observed in 531.5, you will find out there is OHO, right? And so if that O is gone, then OH has been reduced, right? And so that band has been reduced, and therefore this kind of peak as observed is 531.5. So that is the oxygen. We can treat it as a vacancy of the oxygen or absence of oxygen in that particular thing.
Okay. Okay. So I think there is no more questions from the participant side, and I take this opportunity to thank Dr. Praveen Warke for his wonderful talk on two-dimensional material-based photodetectors. So thank you, Dr. Praveen Warke, for a nice talk. Thank you so much.
Thanks a lot. Thank you. Thank you very much.
So now let me invite Lashmi for concluding this section.
Dear sir, thank you so much for the wonderful talk. I would also like to extend my gratitude to Dr. Saji KJ for chairing the session. Thank you, sir. Next, we are moving on to the poster presentation session. The Zoom platform has